All right. Hi, year 11s. This is Mr. Lim here, and today we're going to be doing a video about energy profile diagrams. So let's go find out some more. All right. So we have done energy profile diagrams before. We've done them when we did exo and endothermic reactions. Okay, so let's go through what we need to be able to do by the end of this video. Label an energy profile diagram, determine whether it's endo or exothermic, what it's showing. Recognize pieces of text, so like you read the text and you work out what does that information say about this energy profile diagram that you're about to draw. Describe what the transition state is, draw an energy profile diagram, and interpret an energy profile diagram to gather information about that particular reaction. Okay, so that's what we are going to be doing in this video. So energy profile diagrams, what are they? So energy profile diagrams show the change in chemical potential energy or enthalpy of a reaction. Okay, so there are some general characteristics of energy profile diagrams. Okay, so every time you see energy profile diagrams, you'll be able to work out certain things, and these are some of them. So first of all, enthalpy of the reactants. Okay, so enthalpy of the reactants, what does that mean? Okay, so here's energy profile diagram. This is the enthalpy, right, or chemical potential energy, and we're going to be able to see that we can see where the reactants are, which are here. All right, the reactants, they have a certain amount of chemical potential energy. All right, so that's the chemical potential energy or the enthalpy of the reactants. Okay, so that's the enthalpy of the reactants. Tick. Okay, oops, tick. Okay, so then we're going to be looking at the enthalpy of the products, which will be the exact same thing except for the products. So they're over here. That's the enthalpy of the products. And so you can see here that the products have less enthalpy than the reactants. That's not what I meant to be writing. Products is less than the reactants. Okay, and that will mean something later, and we'll discuss that later on. Okay, however, so that's now enthalpy of the products. Okay, next is the transition state. So what's transition state? Transition state is here. Okay, so this is the transition state. Transition state. Okay, that's where that is. Okay, it is the point where all of the bonds of the reactants have been broken and they've yet to be put back together, and we'll be discussing that later on. Okay, that's the transition state. So we did that. Yep. Okay, activation energy of the forward reaction. Okay, labeled as EAFWD for a activation energy of the forward reaction. So let's have a look at what that is, where that is. Okay, the activation energy is the energy required to break the bonds between the reactants and bring it to the transition state. So it is this amount here from the transition state to the reactants. That's the activation energy, EA forward. Okay, that's the amount of energy required to break the bonds. Okay, so that's the EA forward. Okay, we did that. And then we can also label the activation energy of the reverse reaction with EA reverse. Okay, and that is really more for year 12, but the concept is it's the same thing, except when you go from products to reactants, it's going to be here to here. That's the EA of the reverse. Okay, the reverse rate of reaction or reverse reaction. Okay, so that's the other activation energy. We did that. And then finally, the change in enthalpy, which we'll do in yellow. Okay, and so what is that? That's the change between the reactants and the products. Right, that's the change in the enthalpy there, and that will be labeled as delta H. Okay, so you've probably seen all of those before, hopefully in when we did exo and endothermic reactions. Okay, so those are all of those. Let's go try that again on another one. Okay, so here, let's label out our reactants and products. So reactants can be labeled with R, P for products. Let's label our transition state. Where's that? That's over here, transition state. Okay, make sure that you use an arrow, right, to point out the exact point and to make sure that you're actually pointing it out. Okay, if you just had an arrow that kind of sat there, that is not good enough. Okay, you've actually got to make sure that they touch. Okay, let's go do the activation energies for the forward and the reverse rate of reaction. Again, you've really got to make sure that you are showing exactly where it goes to. Okay. This is the EA of the forward. Okay. If you were to do something like this, where you're like, oh yeah, that's the activation energy of the reverse, that would be wrong. Okay. So let's go, erase that. All right. And let's put that back and let's put it properly. So it's got to go all the way to the top. Yeah, that's not even very good. And all the way down to the bottom. Okay. And so that is the EA of the reverse. Okay. And then finally, the delta H, it'll be from the products to reactants or difference between those two. Okay, so that's the delta H. Okay, so that's how you label an energy profile diagram. Let's move on. Okay. For a successful collision to occur, the particles must have sufficient energy, i.e. activation energy, to break the bonds holding them together. What are the other two things that they need to have? A collision and a correct orientation. Okay. This energy comes from the kinetic energy of the substance, which is measured by its temperature. The kinetic of the energy of the substance is not shown in this diagram. We'll be talking about that in the next video, in the next diagram. However, if the the temperature determines if the particles have sufficient energy, and so therefore, if we can read certain things and work out whether the activation energy will be high or be low. Okay, so if the activation energy is low, then the reaction can occur at room temperature, which is a relatively low temperature. And so it will seem to react spontaneously or as soon as the reactants start to collide. Okay, so effectively, if you read a piece of text and it says, okay, well, the reaction occurred spontaneously, okay, then you can say, well, it's occurring at room temperature or at the temperature that it's at. And so therefore, it's probably got a low activation energy. And if you were to draw it out, you would have to draw it out with a low activation energy. Okay. If the activation energy is high, okay, if the activation energy is high, then the reaction will need more energy from an external source. It might be that you're using a fire or an igniter, all right? So fire or the substance has to be warmed before it reacts, okay? And that will indicate that the activation energy is high. And so when you are drawing it, you need to be able to say that, okay, that activation energy is high, so I'll draw it so it's high, okay? So that's turning text into information. Let's move on. Energy profile diagrams. Okay, so once the bonds are broken, the reaction atoms are in a transition state. So now we're talking about transition state. Okay, so meaning that they are free from all bonds and able to form new bonds. Okay, so if they are in the correct orientation, they will form new bonds with other reactant particles. If they're not in the correct orientation, they will go back to their reactant forms. Okay, so let's just imagine, oh, whoops, let's go draw that in with pens. Okay, so imagine I have H2 here, and then I have Cl2 here. Okay, if they react in this orientation, they're going to break apart, okay, and then turn into 2 hydrogens there and 2 chlorines there, okay, and then maybe if they collide like this, the new bond will form over here, and they will form 2 HCl's, okay, so HCl. But if these things react in this way, over down here, if they bump into each other going this way, which is not going to be very useful, right? When they separate, maybe these two will be close to enough to one another to make a bond, but the other two aren't, and so therefore it's not really going to react in the right way that it's supposed to. Okay, so therefore this one is probably not going to work, and this one is going to work. Okay, but the idea is that the transition state is when the atoms are in their individual states and they have yet to form bonds. Okay, the formation of new bonds, oops, that's not my one. Okay, let's erase that. The formation of new bonds releases energy. Okay, and it's really super important to remember that the formation of new bonds releases energy. Okay, because bond breaking requires energy. Okay, so you need to use energy to break a bond, but the formation of a new bond releases energy, which is why the chemical potential energy reduces after the transition state to the products. Okay, so what does that mean? Okay, So from the transition state, as it goes down, okay, that enthalpy drops because it has lost chemical potential energy, okay? And that chemical potential energy is turned back into kinetic energy or some other type of energy. And so therefore, you have the idea that it releases energy, okay? So whether the energy released during bond formation is greater than or less than, okay, so greater than or less than the energy required to break the bonds determines whether it's an endo or exothermic reaction. If the energy released during bond formation is greater, so released is greater, then it's going to be exothermic. If it is, if the energy released is less than the energy required, then it's endothermic. Let's have a quick look at these two things again. Is this endo or exothermic? Okay, so the amount used going up here is less than the amount produced over here. So therefore, this is endothermic. Okay, and no, where do I go? That's the one I wanted to go. That one's endothermic, and this one is exothermic. Oh, exothermic, because it is producing enough energy as it goes down here. So producing energy here, and it's consuming energy to get up there, right? Okay, so that's that one there. Okay, endo and exothermic reactions. We did a lot of those before, so hopefully you remember how to do that. Okay, when drawing energy profile diagrams, a couple of things to remember. You draw the activation energies and change of enthalpies to scale to one another. Okay, so change in enthalpy, that's your delta H, and your activation energy, you have to have them to scale. Okay, so therefore, if you've been given values like 100 and 200, then one of them is going to be double the size of the other, or half the other size of the other. All right, do not put values on the enthalpy scale, all right, because they don't really have values. Changes to enthalpy have values, but the absolute amount of enthalpy in the reactants and products is unknown. Okay, so changes can have value, but the amount of enthalpy of the reactants and products is unknown. And then the horizontal scale, okay, is the progress of reaction, okay, not time, okay, because the transition state is only present for an instant, and so therefore, if you were to really have it in terms of, time, okay, it'd be reactants, products, transition state goes all the way back down to products, okay, and so that time isn't really a very good indicator. It's actually rather better to say progress of reaction. So this diagram that I've actually used is actually a terrible diagram, okay? Lots of things. First of all, you don't want all of this stuff here, all right? It's there so that you can say that, okay, well, then that one here is 50 kilojoules, okay? And remember, what's this one? This is delta H. Then you've got the activation energy here. EA forward would be how much? 200 kilojoules, okay? So, you should rather label these values rather than putting it over here. That should definitely not be here. Okay, you should just have this as enthalpy or H. Okay, and this one here shouldn't say reaction pathway, it should just say progress of reaction, but definitely shouldn't say time. Okay. Okay, and that is it. Sorry for the long video. The next one will be shorter, hopefully. Adios.